The final item on the agenda of this course is the transform that we call the Z transform. The Z transform has many analogies with the Laplace transform. In fact, the process by which I will treat the subject will go more or less through the same steps and often include the same remarks, except for the addition of drawing analogies with the Laplace transform that I did when I handled the Laplace transform. So, there are too many things in common, and yet there are some significant differences in appearance. However, if one is able to get beyond the superficial similarity, the differences, one does see that there is a lot of commonality between the Z transform and the Laplace transform. So, let us start by telling you what it is. The Z transform is the counterpart of the Laplace transform for discrete time signals. For discrete time signals, that is to say that the ZT, as I will abbreviate it to, is to the DTFT what the LT is to the CTFT. The reasons we have invented a Z transform are also similar to the corresponding reasons we gave for the case of the Laplace transform. One way of looking at it is that we can make the frequency complex. So, instead of frequency from frequency omega, where omega was in was from 0 to 2 pi, we move to Z given by r e to the j omega, where r is a real number in the range 0 to infinity. Clearly, you can see from what I have just written that even r equal to infinity and r equal to 0 I have considered, which is unusual for normal mathematics. All right. So, this is one way of looking at it. The other way is to recall that the DTFT does not exist. The DTFT does if xn is not absolutely summable. Right, that is, if summation over all n of mod xn is not finite, then the DTFT may not exist. But the Z transform is so defined that it may exist even for such a signal. Basically, we ask the question, can we seek to find the DTFT of a non absolutely summable sequence by modifying it through multiplication with a real discrete exponential. The expectation is that the modified signal will be absolutely summable even if xn was not. So, that is the idea, whether we can somehow arrange this. Now, let us quickly go through the appearance of different kinds of discrete real exponentials for different values of the parameter. Now, the general discrete exponential is written as xn, discrete real exponential is xn equal to r to the power n, fine, for minus infinity less than n less than infinity. So, this is where, and r is r 0 less than equal to r less than equal to infinity, right. Now, let us make some few plots. First, for r greater than 1, r greater than 1 you have r to the power n. So, at n equal to 0 this will be equal to 1, and for positive n it will increase rapidly, for negative n it will decrease exponentially. So, you have and so on, and on this side you have this is r greater than 1. Next case, which we will plot on the same graph for comparison, is r lying between 0 and 1. When r lies between 0 and 1, 1 by r is greater than 1, and thus what you find is 1 by r to the power n is a sequence of the sort we have just drawn, and r to the power n is the reciprocal of these values that we have plotted over here. In short, it will be tall for values of n less than 0 and short for values of n less than greater than 0. as n goes towards minus infinity, it will blow up exponentially and get exponentially infinitely large. As n goes towards plus infinity, it will get smaller. So, you have this. So, this is 0 less than 0 less than r less than equal to 1. What about r equal to 1? When r is equal to 1, you get that curve which lies exactly in between these curves, which is the fixed sequence, the let us say the constant sequence So, you see how the tops of these three varieties for r lying between 0 and 1 and beyond 1 are shown. So, this is as far as positive values or non-negative values of r are concerned. What happens when r is 0? When r is 0, 0 to the power n is identically 0, there is nothing to discuss. Next, we talk about what happens when r is negative. When r is negative, you get sequences that look like what we have already drawn, but they are alternating in magnitude. So, thus for r less than 1, what you get is a number like say minus 2. So, minus 2 to the n increases in magnitude as n increases and decreases as n goes towards negative infinity, but it alternates from 2 to the n to minus of 2 to the n to plus 2 to the n minus 1, and it keeps changing in sign. So, you have this. For n 0, it is of course this, then it is this, then it is this. This is for r less than 1. What happens if r lies between 0 and minus 1? There is a small correction I am making over in this place, 0 less than r less than minus 1 less than 1. Here I am now going to plot, well, if I continue this plot towards the left side of the axis, I would get this for, I am drawing for r less than 1. Sorry. So that it has a pair of envelopes like this. This is for r less than 1. Now we move to r lying between 0 and minus 1. So, minus 1 less than r less than 0. You would now have 1 by r, mod 1 by r greater than 1. So, you would get a curve similar to this, except that it gets flipped along the time axis, about the time axis. So, you get an upper and a lower envelope like this. That is what you get. But both these, as you see, are alternating. Now, the last case of what happens if you take r equal to -1. Here also we have plotted, sorry, we will use a different color. When r equals -1, you get an alternate pattern of pulses, all of magnitude unity, but continuously reversing sign. So, this is r equal to -1. So, we have all these information now about how real exponentials, discrete exponentials look when they are subjected to various values of r. Now, let us make the formal definition of the Z transform. X Z as it is called equals the summation over all n of x n z to the minus n, where z equals r e to the j omega 0 less than equal to r less than equal to infinity, 0 less than equal to omega less than 2 pi. That is the Z transform. Now, we can therefore rewrite it as equal to summation over all n x n r to the power minus n e to the minus j omega n, which equals summation to the power over n of x n r to the minus n e to the minus j omega n, which is simply the dtft of x n r to the minus n. This is what we said when we claimed that even if x n does not have a dtft, x n r to the minus n, the modified function, might have a dtft. So, the modification is being carried out by means of a multiplication with a real exponential. Exactly what we did in the case of the Laplace transform, where the real exponential we multiplied with was e to the minus sigma t. Here we are multiplying by r to the minus n. Fine. So, at all times let us not forget that the Z transform is the DTFT of a modified version of the original xn. So, now having seen this much of it, we will see if we can compute the Z transform for some simple functions. For example, let xn be equal to a to the n un, which is a right sided exponential sequence. We have this right sided exponential sequence. So, let us just substitute it in the expression and see that x z equals summation over all n a n z to the minus n which is equal to summation over all n greater than equal to 0, because there is un over there. Un should have been written over here, which is now no longer required. So, you write a by z to the power minus a by z to the power n. This is a geometric progression. And the series will converge only for a by z mod a by z less than 1. When it converges, the infinite sum will be 1 by 1 minus a z inverse, which is nothing but z by z minus a, or 1 by 1 minus a by z. This is what we have. So, now let us see, we have an expression for the infinite sum if it converges. Now, when does it converge? It converges when a by z is less than 1. Now, when is mod a by z less than 1? A is generally complex, right, and a by z, for mod a by z to be less than 1, we need to ensure value of r equal to mod z must be greater than mod a. Mod z must be greater than mod a. So, this defines what is called the region of convergence, the set of points, the set of values of z for which the z transform exists. Right. Now, this is called the region of convergence. This is the ROC, the concept of the ROC is very much analogous to the corresponding concept in the case of the Laplace transform. Just as was the case with the Laplace transform, we will largely confine ourselves to time functions which are exponentials and relatives of the exponentials. But before we study more examples, let us just examine a fundamental property of the Z transform that also corresponds to a similar property with the Laplace transform, namely how it handles the sum of multiple component functions. That is to say, if x n had a Z transform of x z, sorry, if x1n had a z transform of x1z and an ROC of R1, and x2n had a z transform of x2 z with an ROC of R2, then x n equal to x1n plus x2n will have a transform of x1z plus x2z, and the ROC is usually equal to R1 intersection R2, but not always. More on this later. More about the exceptions at a later point. So, all we have to note right now is that there is an ROC in addition to the algebraic expression of the function. Now, let us look at a plot of the ROC of the Z transform, just like we had made plots of the ROCs of the Laplace transform of a function. In the case of the Laplace transform, we had rectangular coordinates sigma and omega, sigma along the horizontal axis, omega along the vertical axis. Now, for the Z transform, it turns out to be more convenient to use a polar format, a polar coordinate system, where we have omega along the rotational axis and r along the radial axis. So, we have the Z plane and in the Z plane a very important entity is the so called unit circle. Is the set of points satisfying mod z equal to 1 or simply r equal to 1. It is a circle of radius 1 about the origin. That is mod z equal to 1. That is the unit circle. Now, this is the point at which r equals 0 and r increases radially outward like this, and omega increases like this. This is the value of omega at for this point, and omega changes is the angle in the polar coordinate system. That is omega. So, now given one ROC and another ROC, we can try to see how to plot them. If we take the first example of the problem we have solved, where a was a certain complex number and we found that the ROC corresponded to mod z greater than mod a. Let us say that a is over here. Let us say that this is a. This point that we have marked with a cross is a. Now, this has some magnitude whose value is given by this. And to say that the region of convergence includes all points on the z plane for which the magnitude is more than the magnitude of a is to be able to draw a circle of the radius of a and then to mark by shading all points outside the circle as the region of convergence. So, the green area is the ROC. Now, if you have two functions like we had in the last example where you had x1n and x2n, let's make that example a little more concrete. Let's say that x1n equals say 2 to the power n un and x2n equals 1 by 5 to the power n un. Then clearly we have x1z equals 1 by 1 minus 2 z inverse and 1 by x2z. So, this is equal to z by z minus 2, x2z equals 1 by 1 minus 0.2 z inverse equals z by z minus 0.2. We can see two things. First, that the individual transforms are ratios of polynomials in Z. That's the first observation to make. The second observation is that this 1 and 2 exponential term the expression for xz contains a 0 numerator root at z equal to 0 and a pole which is a denominator root at z equal to a, whatever is the value of a, 2 for x1 of s and its 1 by 5 equal to 0.2 for x2 of s. So, there is always a pole and a 0, both these things are there and it is in polynomial rational form, just like was the Laplace transform, right. So, now with these two things we will now look at the ROCs. The ROC of XS must be obtained with a knowledge of the ROCs of x1z and x2z. Now for this we have r greater than 2, here we have r greater than 0.2. This is the ROC for this is the ROC for this, right. Now we will see, thus then the ROC here is intersection set of all points, is the set which is the intersection of the set of all points z for which mod z is greater than 2 with the set z for the set of all points mod z greater than 1 by 5, which equals the set containing those z for which mod z greater than 2. Thus, if we go back and draw the ROC, well, there is no place over there, so we will make a fresh diagram. We will draw the poles, the zeros, as well as the ROCs of the individual terms and the ROC of the overall term, overall expression. Let us draw the unit circle first. So that is the unit circle, mod z equal to 1. Then you have a pole at z equal to 2. So you have a pole over here. The pole is represented with a cross. There is another pole at 1 by 5. Sorry, let me just redraw this diagram. The scale is not convenient. The unit circle mod z equal to 1, this is 1 and this is 2. So you have this is mod z equal to 2. The ROC for the second expression extends beyond this, for not for the second expression, for the first expression, r x1s, this is for x1s, which is therefore called r1. So this is for R1. Now if you try to plot R2, R2 will be this. At 0.2 you have to draw a circle, and it will be all things radiating out from here. Clearly, the ROC of the combination is the intersection of the individual ROCs, which comes to this. This is what we have just proved, and this explains a lot of things. Now we have a pole over here. I will mark it with a different color. There is a pole over here in yellow. There is another pole at 2 over here. This is the second pole, and then there are two zeros which I will mark in red right at the origin. Two zeros at the origin. Well, so much for the figure. It's a little so-so because of a rather poor choice of values of the pole positions. We should have had more moderate values rather than such large and such small values. Next thing we introduce is also similar to what we did in the case of the Laplace transform, issues of ambiguity of the Z transform. Consider xn equal to a to the power n u minus n minus 1. Fine. This is now a non-causal sequence, non-causal exponential sequence. Now let us see if we can find the Z transform of this. Xz equals summation, because there is u minus 1 minus n minus 1, it is summation from minus infinity to minus 1 of xn z to the minus n, which equals summation minus infinity to minus 1 of a n z to the minus n, which can be written as, taking n dash to be minus n, this will become 1 to infinity of a to the minus n z to the n, which is equal to summation, this is rather, it's equal to 1 sorry, just one second. Summation 0 to infinity a to the minus n z to the n minus 1, because for n equal to 0 we actually do not have the term in this expression over here, but we are including that in this expression over here. Thus, you get after simplification, this expression we know how to expand. So, after we simplify everything, this comes to xz equal to also 1 by minus 1 by 1 minus a z inverse, which seems to suggest that if we had chosen xn equal to minus a n u minus n minus 1, then we would get the negative of this as xz, we would get xz equal to 1 by 1 minus a z inverse, which is identical to what we got for a different expression a little while ago. However, remember that whenever we get an algebraic expression form for xz, it inherently says within it that this is valid only for those points z where it converges. Now, let us see for what points z this will converge. It will converge where the summation z by a, as seen from this part over here, will converge. What we are essentially summing is summation z by a to the power n. Now, when will z by a to the power n converge for positive n? Because we have now changed variables over here and it is positive n. It will converge only where mod z is less than mod a. That is to say, the region of convergence is mod z less than mod a. So, the expression is the same as for the earlier term, but the ROC is different. Let us collect the two examples together and write it down. So, for x n equal to a to the n u n, you get x z equals 1 by 1 minus a z inverse z greater than mod a, which is what we plotted a little while ago, and for x n equal to minus a n, a to the n, u minus n minus 1, which is the anti-causal sequence, exponential sequence, you get x z equal to the same thing as before, 1 minus a z inverse, but now we have mod z less than mod a. So, summary is as follows: more than one time sequence x n can have more than one time sequence can have the same expression for x z. Two, more than one time sequence can x n can have the same expression for x z. Second, if we consider both items of information the expression itself of expression of x z itself as well as the ROC, if you consider both these, then the ZT is still unique. That is to say, only one discrete time signal will have a particular xz as well as the ROC given. So, that puts things in perspective, and the perspective turns out to be exactly the same as for the Laplace transform.